Hello, George Romanic here. Before explaining the main topic of today's video, I would like to inform you that the next video will be on the great Boltzmann distribution, which describes the probability that a system of particles will be in a given state as a function of the energy of that state. You will see it is absolutely breathtaking achievement of mathematical physics and statistical mechanics. But to arrive properly at that theory, we need to know a little bit of mathematics. And that mathematics is known as the Lagrange Multiplier technique. And that's the main topic of today's video. What is the Lagrange Multiplier technique? That is a mathematical technique that we use to find maximum or minimum of a function given one or more constraints. Imagine you have a multivariable function and someone asks you to find extreme, but not overall maximum or minimum, namely absolute maximum or absolute minimum, but to find maximum or minimum in a certain domain, which we would say given certain constraints. Technique that tackles that problem is called the Lagrange multiplier technique. The best way to describe this technique is to demonstrate how it works on a particular problem. And in today's video, I will use a problem of extratropical cyclone, which is a low pressure system, and we will assume we need to travel through that system and we need to find the minimum pressure along our road, along our route. So not the overall minimum in the center of that cyclone, but along the road that we will take. Let us see how the Lagrange multiplier technique helps us to answer that question. Let us say you want to travel from Montreal to New York. And we can approximate this road as a straight line because approximately New York is south of Montreal. You sit in your car and you want to traverse this distance. However, on the news they tell you there is a strong mid-latitude cyclone with the center west of this road, and let us say the center is somewhere here. Low pressure system. Here we have one isobar, let us call it isobar P, and then perhaps here is another isobar P plus delta P, where delta P is increment of pressure, so you can see pressure is decreasing as we are going towards the center of this system. Here is perhaps next isobar, and as you can see, this pressure system is crossing your road. Perhaps center of this pressure system is close and you can expect severe weather. Now, of course, you could ask yourself a question. What is the minimum value of the pressure that I will encounter traveling from Montreal to New York? Important to note is we are not interested in the minimum value of pressure in the center of this cyclone, but on the road between Montreal and New York. Lagrange multiplier technique was developed to tackle these types of problems. So the pressure field as a function of spatial coordinates x and y is the function for which we want to find minimum, and let us call that function f of x, y, and we usually call that function objective function. This straight line is the so-called constraint, and let's call that function g of x and y. So the question is, find the minimum of the objective function given the constraint g of x and y. Let us quickly examine this problem with a little bit better graphics to get better physical intuition and mathematical intuition to what we want to do, and then we will come back here and do it mathematically. This simple script should help us visualize what do we mean by Lagrange multiplier method. If I run it, you will see this function that has a bell-shaped, and it serves to represent an idealized low pressure system with the lowest pressure in the middle of this bell-shaped function. At the same time, we have this thick black line that represents road from Montreal to New York. And the question is, what is the minimum pressure that we will encounter when we travel along this road? It might be somewhat easier to visualize this if we project this black line onto the surface of our function f. And that's what this command over here will do. So if we go back now to this figure, you will see that this dashed dotted line is the projection of the thick line onto the function f. And we can see interactively with our eyes that the minimum value of the pressure along this road, or formally saying along this constraint, is negative 0.0482 and so on. So we better get this result at the end of our video when we do this using pencil and pen. Sometimes it is even easier to visualize this in 2 dimensions, like now we have x, y coordinates, and here these colors are the values of our function. And you can see this black line is the road. And once again, we can see that the minimum value of our function sits somewhere here. Now, when we have better understanding of 2D and 3D representation of this Lagrange multiplier technique and what the problem asks us to do, let us go and do it. Here is a figure that I just showed on computer screen, but here I printed it in a different form. I printed it with ISO lines of the constant values of our objective function f, x and y coordinates, and here this black line is our constraint. My printer is running out of color, as you can see, but it will not prevent us to do this beautiful mathematical problem. Now, if you look into these ISO lines, notice that, let us look into this one. Notice that this ISO line is curving like that, and basically it is touching our constraint in this point over here. And this is clearly the minimum that we want to find. This is the minimum of the pressure, in this case, on this road between Montreal and New York. Now let's focus on the shape of this ISO line of our function f of x and y, and how it touches this constraint g of x and y. Namely, what we saw is this ISO line of our function f. Here is the center of our cyclone, and we had our constraint like so. What Lagrange realized, which is really ingenious, is the following. If we calculate gradients of our objective function f and gradients of our constraint, they will look like that. Here is the gradient of objective function, and I will shortly explain what gradient is from the physical point of view. But you can see already that gradient is always normal to the ISO line of the function and points towards the fastest change of a function. And you can see from, if we go back here, that indeed the fastest change is perpendicular to the ISO line of this objective function f of x and y. And we call this nabla f, gradient of f. Now we calculate gradient of this constraint g. Maybe gradient has this intensity, namely this length of vectors. This is nabla g. Of course, gradient operator nabla is equal delta delta x in one-dimensional case. Nabla is equal delta delta x delta delta y in two-dimensional case, and nabla is equal delta delta x delta delta y and delta delta z in the three-dimensional case, and you get the point if you want hyperspaces or hyperdimensions. But if we go back to this figure, notice that there is only one point in this figure where nabla f is parallel to nabla g. And that point is this point over here. And let us call that point xp, yp, where p stands for peak, because that's the peak of the pressure that we want to find on this road between Montreal and New York. From this figure, we can clearly conclude that gradient of f evaluated at this point xp, yp is proportional to the gradient of constraint that is evaluated at this point xp, yp. I purposely drew these vectors to be different length because I don't want you to think that these gradients need to be the same in terms of intensity. Perhaps this one is larger than this one, but at this point over here, they are pointing in the same direction, which means they are linearly proportional. To go from proportionality to equality, we do what we always do. We introduce constant of proportionality. And that's what Lagrange did too. He said nabla f evaluated at the point xp, yp is equal, not proportional, equal constant of proportionality lambda nabla g evaluated at this point xp, yp. And this, my dear viewers, is called Lagrange Multiplier technique. And this lambda is called Lagrange Multiplier. So I hope that what we did here demonstrated to you both graphically, intuitively, and conceptually over here, as well as over here, what the Lagrange multiplier technique is really all about. When we know all this, let us go back and actually calculate now this problem. Let us put this theory to work. Our function f of x and y is bivariate normal distribution, which is in the form 1 divided by 2 times pi sigma x sigma y times e to negative. So here we have x minus mu x squared divided by 2 sigma x squared and plus y minus mu y squared divided by 2 sigma y squared. And to make this more similar to low pressure systems, I added minus over here to have it, so to speak, like a negative bell-shaped function. Sigma x and sigma y are standard deviations of our variables x and y, and mu x and mu y are the mean values of our variables x and y. And in this particular problem, I decided to have mu x equal mu y equal 0. And of course, you can see that on this graph because the center of this function is positioned at x equals 0, y equals 0 right here, which is, so to speak, the center of our low pressure system. Moreover, I used sigma x equals 2 and sigma y equals 1. And that is why this function is skewed in one direction. It's not perfectly circular, but it's more elliptical. Well, with these particular values, if we go back to this objective function, we get that f of x and y is equal minus 1 over 4 pi. 2 times these 2 give us 4 pi because sigma y is 1, e to negative x squared divided by 8 plus y squared divided by 2. Our constraint function is simple straight line x equal 2. As you can see from this graph, x equal 2 is this black line. Or we can write that x minus 2 is equal 0, and therefore our constraint g of x and y is equal x minus 2, this function. I want to formally write it g of x and y, but you can see this function doesn't depend on y to begin with. Now when we have objective function, we have constraint, we can write our theory that nabla f is equal lambda nabla g, or in terms of column vectors, for example, we could write this nabla f as delta f delta x delta f delta y is equal lambda. Column vector of this is delta g delta x delta g delta y. And now we have to get dirty and calculate derivatives of this function f with respect to x and y. Delta f delta x is equal, so that will be negative 2x divided by 8, but 4 times 8 is 32, and that 2 will give me 1 divided by 16 times pi, and then this exponent negative, I will for shortness just put this like that, knowing that it needs to be whatever is in this bracket over here. Delta f delta y is equal, again it will be negative 2y, and that 2 and this 2 will cancel, so I will have, here is x, sorry. So I will have y divided by 4 pi times e to negative, and again the same term in this bracket. Now derivatives of our constraint couldn't be easier. Delta g delta x is just 1, and delta g delta y is 0, because this function is not function of y. Now we use these derivatives to form system of equations. Our system of equations is that x divided by 16 pi times e to negative this factor in the brackets is equal lambda times 1. The second equation is that y divided by 4 pi e to negative this factor in the bracket is equal to lambda times 0, which of course is 0. But notice that here we have now two equations with three unknowns. We have x, y as unknowns, but we also have lambda as unknown. And the third equation that closes the system is always equation for constraint, which in our case is simply x equal 2. That is our constraint. So now we have this system that we need to solve. Of course, third equation is already solved, x is equal 2. Well, that was easy. Now we will take this solution and plug it in equation number 1 and equation number 2. And that will give us, when I plug x equal 2 here, that 2 will cancel with 16 and I will get 1 over 8 pi e to negative. The exponent upon substituting x equal 2 becomes 4 plus 4y squared divided by 8, and that is equal lambda. The second equation becomes y divided by 4 pi e to negative 4 plus 4y squared divided by 8 equals 0. If we now focus on the second equation, we can see that the right-hand side is 0, but we have a factor multiplying exponential function. An exponential function can never be 0, which means this equation over here can only be 0 if y divided by 4 pi is equal to 0, and that can only be if y is equal to 0. So we found x, we found y. Let us now find this Lagrange multiplier lambda. We take these two values, we plug it in the first equation, and we get, I will write it here, that 1 divided by 8 pi e to negative y0, so this disappears, 4 divided by 8 should be 1 over 2, is equal to lambda. And basically this is now a solution for lambda. We can make it a little bit nicer. We can write that lambda is equal 1 divided by 8 pi times square root of e. And if you want this in numerical values, I did the calculation, it's 0.02413331. So we have our lambda as well. What is extremely important, of course, to recognize at this point, that these x and y, as we mentioned before, are the values of our independent variables that we called peak values. The values where the gradients of the objective function and constraint function are proportional. So to find the value of our function using these inputs, we say that f of xp yp is equal negative 1 over 4 pi times e to negative 1 over 2 plus 0 squared over 2, and that is equal negative 0.0483. Some of you might say, well, how did you get this over here? But I know that my function f of x and y is equal minus 1 over 4 pi e to negative x squared over 8 plus y squared over 2. This result tells us that our mid-latitude cyclone has the minimum value of the pressure on this road between Montreal to New York that is equal this. Logical question at this point is, what happens if we have more than one constraint, if we have two or more constraints. So what happens if we have our objective function, let's say f of x, y, and z, let's say 3 variables, and we have first constraint g of x, y, and z equal 0, and the second constraint, let's say h of x, y, and z equal 0. So this is constraint 1, this is constraint 2. How do we proceed? Well, it can be demonstrated. You proceed pretty much in the same way as in the case of one constraint. You combine these three pieces of information in the following way, that you say that gradient of f needs to be first Lagrange multiplier lambda 1 times nabla g plus second Lagrange multiplier times nabla h. If you had third constraint, it would be plus lambda 3 nabla of that third constraint. In other words, you form linear combination of your Lagrange multipliers and gradients of constraints, and now you solve this system of equations. And the reason I decided to make this video in the middle of my series on kinetic theory of gases is the following. In the next video, we will tackle the great and powerful Boltzmann distribution of energies of atoms in an ideal gas. And in that video, our objective function f will be n factorial divided by n0 factorial times n1 factorial times n2 factorial times 3 dots. And our two constraints will be that the sum of ni, and the sum is over I, needs to be capital N, and that the sum of ni epsilon I, the sum is over I, needs to be capital E. Of course, Lagrange multiplier technique goes beyond atmospheric sciences and mid-latitude cyclones. This technique has wide applicability in different fields of engineering, natural sciences, as well as social studies, and particularly it is often used in optimizing business portfolio of different companies, because you can put constraint of a budget and then you can optimize your company knowing earnings, costs of running business, and so on. In next video, we are going to use this technique to develop the great and powerful Boltzmann distribution, which gives us probability that atoms in a gas, for example in your room, will be in a certain state as a function of the energy of that state. In my not so humble opinion, Boltzmann distribution is one of the greatest achievements of statistical mechanics, mathematical physics, and generally kinetic theory of gases. Every time I see the accuracy of that theory, I get goosebumps, and I can only hope that one day I will develop theory that will be 1/1,000,000th of Boltzmann distribution. Until that video, goodbye.